Alright, so what are inverse functions? So the easiest way to think of it is through seeing that it basically undoes a function. So for example, when you do 2 times 3, you get 6. But if you wanted to turn it back to the 2, you could divide it again. So 6 divided by 3, and that gets you 2 again. So that's your undoing of an equation, and inverse functions does the same kind of thing. So it's usually represented as f negative 1 x, so similar to fx but f inverse, so f negative 1 x. And let's just have a look at an example. So let's just say we've got f of x equals 2x minus 3. Now to find the inverse, we actually need to change this f of x to y. So I'm just going to show this as y equals 2x minus 3, and I'll extend my little line here. And then what we're going to do to find this inverse is we're actually going to swap the x and the y. So I'm just going to show x equals 2y minus 3. Oh, that's a very crap 3, so here we go. And so what you've seen that I've done here is I've just literally swapped these two to then become those two there. It is literally as simple as swapping them. And then we just need to evaluate. So then, therefore, that will give us x minus 3 equals 2y. And then moving y at the front, we could say, therefore, y equals x minus 3 over 2, and that's the inverse. And so basically by doing this process, what we're doing is we're swapping the coordinates. So let's just say we've got a graph and we've go A and B. When we find the inverse, we're literally finding this, where as you would know in graphs, A would represent, or in the first example obviously, A would represent the x coordinate and B would represent the y. And so then that's done the same here, but we've just swapped them. So that's finding the inverse. So let's have a look at this on a plane. So I have a simple graph here. And what I'm going to do is I'm going to create a line along here, which is the y equals x line. And so let's just say we have a function, I'll do it in green, that looks a little bit like this, whatever that function might actually be. And so when we find the inverse, what we'd be finding is a graph that looks a little bit more like this. And so as you would notice is that it actually, if you look on the y equals x line, it's actually a reflection along that line. So maybe let's look at another example. So say we've got another plane here, and we've got obviously our y equals x line here. And let's just say we've got one line that goes like that's maybe like this. Then what we've got is, I'll draw some beautiful arrows onto that. Let's just say let's label that f of x. Then the inverse will be a reflection along that y equals x line, and that'll look something like this. Excuse my crappy drawing. And then we can label that as f inverse x, like that. And what you might notice is that these 2 points would meet up along the y equals x line, because obviously it's an inverse. But let's just say we were finding a particular point on it. Let's just say it's here, and let's just assume that this point, I might just do it in black, so this point there, let's assume that that is, I don't know, x equals 3 and y equals 1. Despite my crappy drawing, we'd find that the inverse would actually give us something along here, where it would end up being 1 and 3, which looks decently close on this graph. So the question now is, can every single function have an inverse? So let's just say we had a graph like this, and we've got a line that goes through here, for example. Now, if we were asked if this has an inverse, the only way we can prove that is if the function is 1 to 1. And what I mean by this is that for every x value, there is a single y value. So we can do this in a few ways. So we can look at this visually and go, for every x value along the graph, there is only one y value, whatever that might be. Or we can do some horizontal and vertical line tests. So if I was to place a line at any point along the graph, is it going to touch the graph vertically more than once? And because in this case, obviously, it's a straight line going down, it doesn't. Therefore, it passes the vertical line test. Now, what about horizontal? So we can do the same thing along here. Does it touch more than once, or is it just single? And so obviously in this graph, for every x value there's one y value, and for every y value there's one x value. So that means this function, or this graph in particular, is 1, 2, 1. So then what we can do is, now what if this graph looked a little different? So let me just draw a line here. So what if, let's say, we had a graph looking like, just change the color to blue. Let's just say it looked like this. Alright. So having a look at the individual parts, we can look at the vertical. So we can see that at no point along it does it touch vertically more than once. So it passes the vertical line test. So we definitely know it's something to 1. But if we were, for example, to try the horizontal line test, we can put a line along here, and it's pretty clear that it touches it more than once. So what we can say in this scenario is that this graph is many, try and fit that in, many to 1. So this means that even though it does pass the vertical line test, but not the horizontal, it is a function. However, this particular graph and this function does not actually have an inverse. So the simple thing you need to know is that a function is only has an inverse if it is 1 to 1, and if it is many to 1, it is a function but doesn't have an inverse. And obviously, if you were to randomly get something that was many to many or 1 to many, you're going to obviously know that if it doesn't pass the vertical line test, it's not a function at all. And just a few other things to keep in mind is that the domain of inverse f is equal to the range of f, and the range of f inverse is equal to the domain of f, and the inverse function satisfies f of f inverse x equals x and f inverse of fx equals x. And then it is worth mentioning that one of the main reasons you need the function to be 1 to 1 is, let's say we had a function, so let's draw the graph here, y equals x, and let's say we had a function that looked like that. If we were to find its inverse, so looking along the y equals x line, which would look a little bit like that, you would end up seeing that this, missed an arrow, you would see that it would not pass the vertical line test, and so the inverse of fx in this case would not actually be a function, and so that's why you need this 1 to 1. Alright, so let's just look at some basic-ish questions to try. So we've got, consider the functions fx equals 4 bracket x minus 1 and gx equals 6 minus x over 2. So what we're going to do first is I'm just going to write what g of x is, which obviously equals 6 minus x over 2. And as we know for these, we need to change that to y. So we say therefore y equals 6 minus x over 2. Now obviously we've got to swap the y and x. So we say therefore x equals 6 minus y over 2. And this will result in therefore 2x equals 6 minus y, and then therefore negative y, so I've just switched the sides now, equals 2x minus 6. And then what we'll do is we'll just get rid of the negative and we'll say therefore y equals negative 2x plus 6, or we could show that as 6 minus 2x. So obviously therefore g negative 1, just to state the question properly, equals 6 minus 2x, like that. So now the next one adds a little bit of composite functions like we did earlier. So what we're going to do is we're going to just first show that in a different format. So obviously we can show that as therefore f of g negative 1, so inverse x equals 4. Therefore, and we'll add the g inverse because we've already done that on the other side. We can say f of 6 minus 2x equals 4. And now we can add in the value for f. So we can say 4 double bracket, because f of x is a bracket, 6 minus 2x minus 1 equals 4, and then we can evaluate this as 5 minus 2x equals 4. And then what I can do to make it easier for me is I can actually move this 4 over there. So instead of multiply, we can do divide. So we can say 5 minus 2x equals 1, which is heaps easier. And then I'm going to move the 1 over there and then that over here. And so therefore 4 equals 2x. And then I'm going to flip the sides a bit, and then we can say that x equals 4 over 2, which we know equals just 2. Alright, so let's just say we've been given two graphs like we have been here, and for each of them we've got to find the inverse graphically. So the best thing we can do right off the bat is to draw the y equals x lines, and I'm not going to label them just to try and keep this as clean as possible for now. And so let's just start with this first one. So we know we've got the 2 and the 5 as the two different points on there. And so obviously, as we know from earlier, what's going to happen with the inverse is those points are going to switch. So, and that's because the 0 and 2 point will end up becoming 2 and 0, and the 5 and 0 will obviously end up also becoming a 0 and 5. And so what we can then do is go, okay, so we know we're going to have a point up here, that's a 5, and a point, let's just say about here, that's a 2. And then so what we can then do from there is we can literally, because it's graphic purposes, is it should look a little bit like that, where both of them end up meeting along this line there because it's an inverse. And so if you tilt your head to look along the y equals x line, you can see a very clear reflection, in a sense, that has swapped both the individual lines. Alright, and so on to the next one. Now this is a little bit trickier because we don't have 2 points we can look at, but we can still create a bit of an inverse. So we've got one really key point, which is that 2 there. So I'm just use the green, I'm going to draw a 2 on the opposite. So if I tilt my head on the y equals x point, I can see that when it's flipped, it will open up about here. We've got a 2 here. And so then what I can draw is at least I know that it's going to pass through that point. So I can then look at that and go, okay, so I know it's going to meet at this circle point here, and it's going to touch that 2 line. And because, I'll just draw this temporarily, we got this point here, which cuts this line, is this will end up being on this side, being a little bit like a thing there. So let's get rid of that for a second. So let's give it a try. Try to draw this. So obviously it will come down there, it'll go across this 2 point, and then it will curve around about like that. And so then that's a reflection on the y equals x line for the second graph. Alright, so for this next question we've got, oh, wrong colour, oh my goodness. We have got f of x equals, and it's a fraction, so we got 3 minus 2x over 4. And so there's 3 parts to this question, sorry. So the first part is finding the inverse. So I'm just going to condense this a little bit. So y equals 3 minus 2x over 4, and therefore x equals 3 minus 2y over 4, therefore 4x minus 3 equals negative 2y, therefore y equals negative 2, no not 2, negative 4x plus 3 over 2. That should be right, like that. Alright, and so the second part of this question is we got to sketch this on a graph. So what I'm going to do is I'm going to create a reasonably large graph here. And so first I'm going to graph the y equals x line, and then what I'm going to do is I'm going to graph the fx graph. And the easiest way we can do this is to simply put the function into a graphics calculator. And so what I can do is I've done that, and it will give me the graph of fx, which looks a bit like that. Close, pretty close. So I can just label that f inverse x, and then just doing a simple reflection along the the y equals x line, or I can look at the graphics calculators. I can just say this one looks a little bit like that, and label that one as well. And you know what I've just done is I've said that that equals negative 1, which it does not. So I can delete that, so that's just fx. And then this one is obviously, this one is, and I've got the wrong side, it's amazing. This one is f inverse x, like that. And then for the third part of the question is we've got to prove that, let's draw some line here, that as one of the rules we discussed before, is that f negative 1 of that x is equal to f of f negative 1 x, to show that it is an identity function. So I've just cleared that to give us a little bit more room. So then to find one of these, so we'll just start with f inverse f of x equals f inverse 3 minus 2x over 2, and that was actually 4, wasn't it? So we can say that over 4, which then equals, and this is where it gets a little bit tricky, create a really big one here, negative 4 3 minus 2x over 4 plus 3, which actually becomes a little easier because we can cancel those two, so then that just becomes negative 3 plus 2x plus 3 over 2, which equals just x. And then that matches the rule as well. And then we can just try this one as well. Negative 1 x, and that obviously equals f negative 4x plus 3 over 2, which equals, do another really big one here, and we'll start with, we can write 4 on the bottom, and then we can put in 3 minus 2, negative 4 plus 3 over 2, which gives us, we can cancel that, 3 plus 4, that's x, isn't it? So 4x minus 3, those two cancel, and this is over 4, which equals cancelling those two, which just equals x. And so therefore, matching the rule and this question, those two both equal x, and so these are equal as well. Alright, so we've got a bit of an interesting one here where we've actually got to find the double inverse of a function. So obviously to do this first we have to just find f inverse first. So what we're going to do is we'll say we've got f of x, which equals 2x minus 5, therefore y equals 2x minus 5, and then for f inverse, x would equal 2y minus 5, therefore x plus 5 equals 2y, therefore y equals x plus 5 over 2. And then we can also just say that f negative 1 x equals x plus 5 over 2. Okay, so now all we can do is completely focus on this final equation there. So what I'm going to do is I'm going to put that into this thing here, which is obviously what we need. So I'm going to show that by starting with just f negative 1 x equals x plus 5 over 2, and then obviously we've got to do the usual thing of saying therefore y equals x plus 5 over 2, therefore for the inverse of this we've got to say that therefore x equals y plus 5 over 2, and you might be able to guess what's going to happen soon, but therefore 2x, grab the x, equals 5, y plus 5, therefore y equals 2x minus 5. And you might see something here, that this is completely the same as what we started off with initially up there. So basically what that is saying is that obviously f inverse again of x equals 2x minus 5. So obviously therefore f inverse of x actually equals fx, and then those double inverses actually cancel each other out. Alright, so this is a bit of a different but interesting one. So what we're doing here is we've got to find which of these individual sets of values represents an inverse graph. So basically we've been given here sets of x and y points along the graph, and so based on these points we're going to determine whether it's an inverse or not. Looking at the first one, we can see that each of these x values ends up resulting in a different y value and vice versa. And so what I mean by that is no value is repeated at all in this sequence. So obviously this is inverse. Now have a look at the one to the right of that. So we've got negative 1, we've got 0 and 1. So obviously these are all different, and we've got 3, 2, and 3 again. Okay, so what we've got here is for 2 different x values, we have the same y value. So it's pretty clear that this one here is not a one-to-one function. So on to the next one, we've got 2, -1, 0, and 1. So they're all different. And we've got 1, 0, 2, 3. And they're all different. So that is completely fine. And then down here, we've got, now this one could be a bit of a trick one. We've got -1, -1, 0, 0, 1, and 1. So it may seem like this could not be an inverse one, but you will notice that for every x value, there is a completely different y value, and these overlap. So it doesn't matter that the x and y points are represented by the same number, but it's clear that this is also a one-to-one function. Alright, so now we've got the function fx equals x squared minus 4. So what we've got to do first is put this onto a graph, and then draw the reflection along y equals x. So I'm just going to draw the y equals x line, and using a graphics calculator is showing that this graph looks a little bit like that. Right, and to draw the inverse, just going to do around about like that, I believe. Yep. But then what we can see here is actually, and if I just label this to make it a little bit more clear, so we've got f of x there, and then we got supposedly the inverse. However, if I was to do obviously a horizontal line test, it's clear that that fails that. But even more so, as a vertical line test, is the f inverse fails that line test. And we discussed this earlier, that means that this is not a function. So what if, for example, we had the same kind of graph, but what if for the fx function, the domain was restricted to x is more than 0? And so what this would mean is that instead of having that full curve, and I might as well put in that again. Yeah, instead of having that full curve, all we're going to have is this. And so I'll add to the question, I'll say where x 1, 0 is the domain. Now, we can clearly see that this newly drawn line passes both the vertical and horizontal line test.